Okay, let's continue the lecture on BJT AC analysis. Basically, in BJT AC analysis, you are required to calculate or to obtain the ZI, input impedance, Zout, output impedance, AV, voltage gain, as well as AI, current gain. So, voltage gain and current gain you can get by dividing the V out over VI, whereas AI by dividing I naught over II. Okay, however, for AI, especially for current gain formula, in the module you can find that the formula is quite complicated to remember. However, we have one simple formula that you only need to remember it so long that you are able to calculate the AV. Okay, by using AV you can get the AI, so you don't have to worry about that much. Okay, in BJT AC analysis we are going to analyze the AC analysis for three circuits: fixed bias emitter stabilizer and voltage divider bias circuit. In AC analysis, it means that we consider what happened when the input supply for fixed bias or emitter or voltage divider are in AC mode. Okay, so like in BJT DC analysis, okay, we assume that the BJT is there with terminal B, C, and E, and you can straight away calculate the KVL at input and output loop section. However, in BJT AC analysis, you need to transform first the BJT into RE model. So in AC analysis, there is a transistor model. We call it RE model. So how can you transform it? Okay, you need to get familiar with it. Okay, because you are going to meet them a lot, especially in chapter 4 later on, and chapter 5 if I'm not mistaken. Okay, so the B terminal here in BJT, okay, you need to connect it with beta RE. Okay, what is RE? This one, beta RE, is not similar to beta RE in DC analysis. Okay, the RE here is the emitter, is the resistor at the E terminal. Okay, emitter terminal. But here, this is R with subscript E. Okay, both are in small letter. It is a resistor value that you need to calculate by using this formula. Okay, this one is not given during exam, so you need to memorize it. Okay, RE equals to 26 millivolt divided by IE. So this indicates that the small RE or RE value here in AC analysis are dependent on the emitter current in DC analysis. Okay, so you need to calculate this one first in order to get the value here, beta RE here, and then connect it to E terminal here. Okay, this is E terminal, and then okay, this one is in the input side. Okay, remember that BJT is a current control device. Which part control it? It is the base terminal. Current at the base terminal control it. The IB current control it. This is at the input part. At the output part, okay, you need to connect it with one independent current source here, which is beta IB. If you still remember, IC, IC approximate to IE, but at the same time, IC is also equals to beta IB. So in this case, this is referring to the beta IB is actually referring to IC current. Okay, but again, this is in BJT. This is the BJT transformation in RE model. So we assume that the current that flow through this is beta IB. Okay, because this is the only way that we can interrelate in between the IB and IC currents. Okay, and then we have here at the collector, at the output section, we have another small resistor. We call it RO, or output resistor. Okay, so we have input resistor here, beta RE, and at output section we have R0. Okay, RO or R0. And then after that, okay, the R0 here is connected to the C terminal. So basically at the input section here, okay, just now I told you that you need to calculate ZI. So ZI is over here. It is looking from the base terminal to the ground. So if you assume that E is connected to the ground, so this is the ZI looking towards the input section. Alright. On the other hand, the output impedance, okay, Z out, is looking to within or towards the output section, which is from the collector side to the ground. Okay, so this is the basic BJT RE model that you need to transform it first. Okay, from there, okay, only then we can start our small signal AC analysis. Okay, in small signal AC analysis, there are several rules of thumbs that you need to remember. Okay, the first one is you have to assume that DC supply in BJT DC analysis that you did just now, that I have explained just now, must be equals to 0. So when it is equals to 0, it means that you need to make it as a ground terminal. Okay, so let me write down here. You can say, in other words, must be grounded. Okay, so the DC supply here, you have to replace it with ground. Okay, and then second assumption is that all the capacitors here during AC analysis must be short circuit. So CI here and C2 here in the fixed bias circuit must be shorted. Okay, so we take an example. This is the fixed bias circuit. I have already write down the ZI looking from the input section. If you still remember, input section at the base terminal, and Z out looking from output section at the C or collector terminal. Okay, so you need to transform it. You transform the BJT first. Just now I already teach you. So this is our base beta E terminal. Since E are directly connected to the ground for fixed bias circuit, so you can place the ground over here or over here, anywhere around this line, the bottom line here. Okay, and then we have beta IB here. the independent current source connected with R0, and then we have our C terminal. Okay, the same drawing at the top here, you just copy it down here. Okay, now you need to have an understanding on how to connect from B terminal to RB and C terminal to RC. Since we know that RC and RB both are connected to plus VCC, but in AC analysis, the VCC, you have to ground it. Okay, since we have to assume it equals to 0. So it's very easy. You understand that VCC is no longer VCC because we're going to replace it with ground symbol. Okay, ground symbol like this, you put over here. So straight away, you connect the C terminal here. Okay, let me put something, the terminal point, so that you clear about that. Okay. So this is C terminal. Okay. Let me change the color. Maybe red and Baltic. So this is C terminal, and then we have B terminal here, and another one, E terminal. So we have C, B, and E. Okay. So at C terminal, it is connected to RC. So we just place the RC here, and another end of RC is connected to the ground. Like I told you just now, VCC is no longer VCC. We have to replace it with the ground symbol. So straight away here, the other end of RC. And then in base terminal, we have RB. So RB, we just connected with RB, and the other end here connected to ground, you flip it, okay, and connected to our ground here. You see, it's very simple. Don't forget to write down the VI and V out. Maybe I forget to mention about the how you need to write down the symbol of IB, IC. Okay, in AC analysis, you cannot write the capital letter I here because IB, capital letter IB, is referring to DC analysis. Okay, we are now in AC mode, so all the I symbol here, you must write it in small letter. So IB, IC, VI, V out. Except for RC and RB, they are only resistors, so we don't interrupt them. Okay, so the rest we are using small symbol. Okay, small letters. So now it's about formula that you need to learn now. So just now, okay, I forget about ZI. Okay, this is ZI. I told you it is looking from base to the ground. So here, base to the ground, this is ZI. And then Z0 is right here, looking at the output section from C terminal collector to the ground. Now, to calculate the ZI, looking from this direction, what ZI sees is RB parallel with beta RE. Okay? Or it is beta RE if RB is much greater than 10 beta RE. Okay, this time around, we have another condition. In DC analysis, you are checking beta RE greater or lesser than 10R2. This one definitely you cannot escape. You have to memorize it. You have to hafal it. Okay. Now in fixed bias circuit, there is one condition, different condition that you need to check. So is it RB is greater than 10 beta RE? If yes, so automatically the ZI is beta RE. So you have two formula here. Actually either one is acceptable, alright? It's just that if you notice that RB is greater than 10 beta RE, then we assume that ZI is equals to beta RE. Okay? Why is that? ZI equals to beta RE when RB is greater than 10 beta RE? Because if RB is too big, the current will not going flow through it. Okay, the obstacles here are too big. The current doesn't want to pass through huge obstacles. Yeah, you imagine like that. So the current will find another way or alternative way and going straight to beta RE. That's why ZI is equals or approximate to beta RE. Okay, I hope that one is clear. Second thing is that the Z out. Okay, Z out or Z naught is looking from this direction. So Z out sees who? Only RC and R naught. This one is not resistor. Beta IB is a current, independent current source. So Z out only sees R naught and RC. So RC and R naught is in parallel, or you can say Z naught is equal or approximate to RC if the R naught is equals to infinity or R naught is greater or equal to 10 RC. You see, in SC and DC analysis, you need to remember the test conditions. Alright. In DC, only one beta RE greater or less than 10 R2, but here in SC analysis, we encounter already two test condition. The first one is RB is greater than 10 beta RE. Now here is R naught is greater or equals to 10 RC. Okay, so if the question tell you the R naught is infinity or R naught value is greater than 10 RC, you just straight away put down that Z naught is equal to RC. It's the same reason why only Z naught sees RC is because R naught is too big. So the current doesn't want to flow through R naught. The current just pass through it. Just pass without through it. Okay. So the IC will go straight towards the independent current source. Okay, that is Z naught explanation. The third one is the AV. So we know that AV is current gain must be calculated by using V out and VI. So V out, okay, this is V out. The equation is beta IB. So V out is measured from the C terminal to the ground. Okay, from here to the ground. So what it says is that the beta IB is independent current times the RC parallel to R naught. Okay, this one is just an Ohm's law. Okay, beta IB is a current times RC parallel to R naught. Okay, I would like to mention that in V out, you have to put minus sign. Okay, negative sign. I will explain later why there is a negative sign over there. Okay, let me proceed with other values. Now for VI is measured from this third point, the B terminal to the ground. So VI is IB, we have current IB current times beta RE. Okay. IB times beta RE. So after that we calculate the AV. So AV is VR over VI. So VR over VI, we can cancel out the IB here. Yeah, IB here. Cancel out with IB here. And then beta we can cancel out. What's left is minus RC parallel to R0 over RE. Or if R0 is too big, you can simplify the equation. It becomes minus RC over RE. The fourth formula is AI. Okay, just now I said to you that AI has a complicated formula. What I write down here is the one that have simplified. Okay, so in fixed circuit, the AI is approximate or close to beta. This is only happen if the R0 is greater than 10 RC and the RB is greater than 10 beta RE. Otherwise, you only have to memorize the first one, okay, the first formula here. AI equals to minus AV times ZI over RC. Okay. Let's do some example here. Try to look in your module, example 3.7, page 88. Okay. Okay, this is example 3.7. Referring to figure 3.59, you need to determine RE, find ZI. Here, the question indicates that R0 is infinity, right? So it should be easy. And then you need to calculate Z0. Also, assume that R0 is infinity. Determine the AV. Also assume that R0 is infinity. And then determine AI. After that, for F, you need to repeat part C until D, including R0 equals to 50 kilo ohms in all calculations, and compare the results. So I have write down here the RE, this is the formula, 26 millivolt over IE, ZI, RB parallel to beta RE, or ZI approximate to beta RE since RB is much greater than 10 beta RE, and so on. Okay, let's have a look into solution. Okay, usually the question will ask you to draw the AC equivalent circuit. If you are able to draw this, you can get at least 3 or 4 marks for this. Okay, usually we provide 3 to 4 marks. So I hope you can or able to draw it without doing any wrong here. Okay, so here I redraw from this circuit. So we assume for AC analysis the VCC should be grounded. Okay, we should grounded this. Transform the BJT here to become beta RE, beta IB, and R0. And then the C terminal, okay, C terminal connected to 3 kilo ohms or RC, and then the B terminal here connected to RB here, 470 kilo ohms. If you notice, R0, I open circuit it, okay, open circuit because in the question says that R0 is infinity. So when infinity, we can assume that the obstacle is too big, so we just disconnect it. You make it as a as a open circuit. Okay, so you draw or label IB, label IC, II, and I naught. Okay, so for DC analysis, okay, for the first question, you need to determine RE. RE is 26 millivolt over IE, but we don't have IE. So you need to calculate from DC analysis. So this one, I'll skip this, okay, because you already did that before. So in this analysis, the IE is equal to 2.428 milliampere. Okay, this one you need to do it by yourself, okay? Do not rely solely on my explanation here. You need to take your calculator and do it by yourself. If not, you will never learn, okay? I only guide you, so you need to try and calculate it, okay? So from the DC analysis, after you obtain the KVL at input section, you can get the IB, and then from there you can calculate the IE. Once you get the IE, you put in the equation, so you will get 10.71 ohms. Okay, this is another tip I want to share. Usually RE will not in a kilo ohms. Rarely I see. Usually it's within in this range, 5, 10, or maybe 20 or 30. Rarely it goes to 100 and above. Okay, rarely, jarang. Okay, usually less than that. If you get very big RE, it means that you did something wrong in your calculation. You need to double check. Okay, please remember what I told you just now. And then we calculate the beta RE. Okay, once you obtain RE, small RE here, you calculate beta RE. Beta is given hundreds, so you will get this value. And then you can calculate the ZI. Here, ZI is equal to RB parallel to beta RE. Suppose that this time around the beta RE is too big. Okay, it should, suppose it this results, this question check for RB, is it greater or equals to greater than 10 beta RE. Definitely is greater. Suppose that the result is not 1.069, you can just straight away take this value as the result, 1.071 kilo ohms. Actually, if you calculate using this way, you will get the similar results, almost not identical, but almost to 1.071. Okay, not far away the value here. Now for Z naught, since R naught is infinity, so the Z out will only see RC. Okay, 3 kilo ohms. So I forgot to put ZI here. Okay, so you have to put it. Okay, let me complete my drawing first. Okay, I have labeled the ZI and Z naught. Okay, so ZI, we already discussed this, and then Z naught, looking from here, it only sees RC. ZI should only look in beta RE, suppose looking beta RE, because RB value is too big. Okay, then we calculate the AV. AV is V out over VI. Since V out is beta IB times RC, and VI is beta RE times IB, we can cancel out the IB and beta, so we only left the minus RC over RE. Okay, let me adjust this one. Okay, so you can see now the AV here is minus RC over RE. Okay, we are using this one here, minus 3k over 10.71k, you'll get minus 280.11. Alright, so that is AV. Now for AI, okay, AI, it says that since RB is greater than 10 beta RE, so okay, let's have a look in my notes here. Okay, since RB is greater than 10 beta RE, then AI is approximate to beta. Okay, I told you that AI got two formula, one, the first one, the second one, but the second one only valid for RB or R naught greater than 10 RC and 10 beta RE. So we just write down hundreds. So if AV is in minus or in negative sign, the AI, okay, the AI should be in positive sign, meaning you will get AI in positive value, AV in negative value. Okay, we proceed the explanation. So now for the F, question number F, okay, you need to assume that R naught is no longer infinity, but R naught got some value which is 50 kilo ohms. So you can check, is R naught is still R naught greater than 10 RC. So RC is 3k, so 3k times 10 is only 30k ohms, but R naught here is given 50 kilo ohms. Still, I think it's quite big. I think there is a mistake here. Let me check in a module. There's some mistake here. Is it true? It says 50 kilo ohms. Yes, it says here. But we need to calculate RC times 10. So I have checked. I think there is a mistake in the module. But anyway, it's supposed that R naught must, if R naught is bigger than 10 RC, okay, we can just use the simplified equation here. For example, Z naught should be RC parallel to R naught. Sorry, it should be RC, only left RC, because R naught is greater or bigger than 10 RC. But anyway, I just explained it. Maybe the reason why it says that because it thought that, maybe the author thought that R naught is less than 10 RC. Okay, you understand me? Never mind, we just proceed, okay? We just assume that R naught is less than 10 RC, so we'll get 2.83 kilo ohms, and then AV here is R naught parallel to RC over RE, okay, and AI. See, I told you the AI actually has a complicated or complex formula, but you can use the simpler one, which is minus AV times ZI over RC. So notice that the negative sign in AI formula. So if you replace the AV with minus AV here, where is AV? Now here, this one, okay, you will get positive sign or positive value of AI at the end. Okay, so you have learned the fixed bias circuit, how to calculate the AC analysis for fixed bias circuit. We will move to the next circuit, not emitter stabilized by circuit. Okay, because in this case it has two conditions: bypass RE and unbypass RE. We will hold that one first because I want to teach the voltage divider by circuit, because this one is the easiest one besides the fixed bias circuit. The emitter stabilized bias circuit is quite confusing, but you don't afraid of it. It's just a matter of learning process. Eventually you will find it very easy. Okay, we will continue after this.